These condensed formula can get pretty long, but that doesn't mean they have to be difficult to understand. Hey there, OChemNinjas. In this video, we're going to go through the 5 levels of condensed formula notation from Ninja Level 1 all the way up to Ninja Level 5. Let's go. The full Lewis dot structure gives us the most information about the structure of the molecule, including all of the bonds and all of the lone pairs. But it's a little bit tedious to draw, and you can imagine before we had computers and we're doing things on typewriters, it would be hard to put in a journal article or on an exam. The condensed formula system is a way to write a structural formula in one line, much like you would write on a typewriter or on a computer. To write the condensed formula, we march down the line from left to right, starting with each carbon, and after each carbon, we put all of the atoms bound to that carbon. The simplest case then is when we have very simple groups bonded to the main carbon chain. The first thing I would do is give the carbon system a numbering to make sure you're accounting for all of the carbons in your molecule. To draw the condensed formula, we start with the first atom in the chain, carbon number 1. We list the carbon, and then we list all the things bonded to that carbon after the carbon atom. There are 3 hydrogens bonded to that carbon, so we would write CH3. The 3 hydrogens are bonded to the carbon immediately preceding it in the condensed formula. Next is carbon number 2. Carbon number 2 is bonded to a hydrogen and a bromine. In the condensed formula, we write those after the carbon. First, we write the hydrogen that's bonded to the carbon, and then we write any branching groups that are bonded to that carbon. For a monoatomic branching group, like a bromine, we simply write the bromine and we move on with the rest of the chain. This says that this hydrogen and this bromine are both bonded to the preceding carbon in the structure. Carbon number 3 is a carbon bonded to 2 hydrogens, so we write CH2 for carbon number 3. Carbon number 4 has a polyatomic substituent coming off of carbon number 4, the OH group. We start with the carbon, we write the hydrogen bonded to it first. For a polyatomic group like the OH group, we put that group in parentheses. The OH group collectively is bonded to that preceding carbon. The parentheses tell us that this entire group is bonded to the preceding carbon. Our last carbon is a CH3 group, so we finish the condensed formula with CH3. This is the condensed formula for this Lewis dot structure. For simple structures with simple branching, we march down the chain and we list the branching groups after the carbon. Polyatomic groups go in parentheses. I'm going to include a bonus work example here to show that substituents that are longer are not more difficult to draw, they're just longer. So we'll start with this molecule. I've already provided a numbering system for this molecule. We'll start with the first carbon. Carbon number 1 is a carbon with 3 hydrogen attached, so we'll start with the CH3 group. Next, we have a carbon with a hydrogen and a chlorine, so we write the carbon, the hydrogen, and the chlorine, just like we did in the previous example, followed by another CH2 group. And next, we have a carbon with a hydrogen and this amine group attached. It's a longer group, but we really don't treat it any differently. We start with the carbon and its hydrogen, and then in parentheses, we put the polyatomic substituent. Start with the nitrogen. The nitrogen has its own hydrogen attached, followed by a CH3 group. This is the polyatomic substituent attached to this carbon. Everything in this parenthesis is bonded to the preceding carbon. And the first atom in that parenthesis tells us which atom is specifically bonded to that preceding carbon. Next is another CH2 group, followed by the next carbon with a long substituent. We have the carbon with its hydrogen, and then in parentheses, we have an oxygen with a 3-carbon chain. So we start with oxygen, CH2, CH2, and CH3, followed by another CH2, a CHF, and another CH2. The last carbon with the substituent is a carbon with the CH3 attached, so we draw the carbon, its hydrogen, and then the CH3, and the molecule finishes with the CH2, CH3 group. These condensed formula can get pretty long, but that doesn't mean they have to be difficult to understand. The second level of condensed formula notation is combining like groups. In condensed formula notation, if we have repeated groups in a molecule, we combine them into one condensed formula so that it's not quite as long to draw out. We'll see several examples of that as we go through this example. Again, I would highly recommend numbering the carbons in your molecule. If we look at the start of this molecule, it starts with a CH3. We could start with the CH3 group. Next would be carbon number 2. It doesn't have any hydrogens of its own attached, but it does have a CH3 group attached. In fact, it has 2 CH3 groups attached. So we could combine these together as one parentheses with a subscript 2, showing that there are 2 CH3 groups bound to this carbon. But you want to be on the lookout for patterns. This is very much a pattern recognition course, and we want to start looking for patterns around the chemistry that we're doing. Not only do we have 2 CH3 groups around this carbon, but we actually have 3 CH3 groups all bonded to carbon number 2. So the way a chemist would almost certainly start this molecule is not this way. Instead, we would start by saying that we have 3 CH3 groups all bound to the same carbon. We're almost like starting with carbon number 2 because all 3 carbons, including carbon number 1, are attached to carbon number 2. Next is carbon number 3, which is a CH2 group. But what I want you to notice is that carbon number 3, 4, and 5 are all CH2 groups right in a row. We can combine those as well. Instead of just writing CH2, 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 we can combine these CH2 groups into parentheses and put that there are 3. This counts for carbons 3, 4, and 5. After we do the 3 methyl groups and the carbon, there are 3 CH2 groups in a row. Finally, we have carbon number 6, which is a carbon, and it has a hydrogen attached to it and 2 of these oxygen chains attached. In fact, both of those oxygen chains are identical. That means we can wrap them up in a set of parentheses. It's a polyatomic branch, so we would start with the parenthesis, and we'd say OCH2, and then we would write the condensed formula for the benzene ring. This is an extra pro tip as part of this worked example, but as part of the benzene ring, there are 6 carbons and 5 hydrogens on the benzene ring. When I say C6H5, in my head, I know that really the only logical way to get C6H5 is to have a benzene ring. So we would say CH2, C6H5. We would combine all of the atoms in the benzene ring together in C6H5, and as a condensed formula, I know in my head that that means a benzene ring structure. This is the polyatomic substituent attached to this carbon. There are 2 of them. We can then take this parenthesis and write the subscript 2. There are 2 of these oxygen substituents attached to carbon number 6. And this is the condensed formula for this molecule, much shorter than the previous one because we were able to combine like groups into one set of parentheses. It is also worth pointing out that combining these groups is not strictly required. You can draw out the entire condensed formula without combining any of the like groups. There's nothing illegal about doing that. It's just much more condensed and much more efficient when you can combine the like groups. These are the same condensed formulas representing the same structure. One is just more efficient than the other. Ninja level 3 looks at the difference between ethers and ketones in condensed formula. We treat them a little bit differently, and if you're not careful, they can look very similar. After numbering the molecule, we can start with the first CH3 group, followed by the CH2 group. Next is the oxygen of the ether. The oxygen is not a branching group. It's not branching off the molecule. It is in that linear backbone of the molecule. So we do not use parentheses when we draw an ether group. We include the oxygen in the linear chain of the molecule. This oxygen is attached to this carbon, which is attached to the CH3. No parentheses because it's in that straight chain. So we just continue on with the CH2 groups. I'm not going to combine these here because that's not the focus of this one. I want to focus on the ketone next. Next, we have the ketone. So it's a carbon that is bonded to that oxygen. It's a doubly bonded oxygen. It's not in that straight chain. We wouldn't really consider it a branching group, but it's sticking up above that chain. It's not in that carbon backbone of the molecule. So we would draw a ketone by putting that oxygen in parentheses, a single oxygen in parentheses. Oxygen makes 2 bonds, so when I see a single oxygen without a hydrogen or another group attached to it, it implies that this oxygen is doubly bonded to that preceding carbon. And then we finish the molecule with the CH3 group. So to call out the difference between the ether and the ketone, a CH2O with no parentheses in the chain of the backbone implies an ether. This carbon makes 4 bonds, the CH3, the 2 hydrogens, and the oxygen. Oxygen makes 2 bonds, one to the preceding carbon, and then continuing on with the next carbon in the chain. With no parentheses, with the carbon with its hydrogens, this is an ether. By contrast, the carbon with no hydrogens drawn and an oxygen in parentheses is how we imply the ketone. Carbon makes 4 bonds. It's bonded to the preceding carbon, the next carbon, and there are 2 more valences, so they must be doubly bonded to the oxygen. Oxygen makes 2 bonds. The parentheses implies that it's branching off of that carbon, and both of those bonds must be implied in a double bond with the carbon. Students often confuse these functional groups in condensed formula, especially if you forget the parentheses on the ketone. Then it looks a lot more like an ether. So be careful when you're looking at these, whether you're dealing with an ether or with a ketone. Ninja level 4 is carboxylic acid derivatives. We start this molecule with the first carbon, the CH3. Carbon number 2 is the carbon involved in the carboxylic acid derivative. It has a double bond to oxygen and a single bond to another oxygen. This is an ester functional group. There is a formulation, there is a convention, a way that chemists write carboxylic acid derivatives in condensed formula. And the convention is based around the fact that carbon is bonded to 2 heteroatoms, one through a double bond and one through a single bond. In this case, both of those heteroatoms are oxygen, but it doesn't have to be that way. The convention says that we write those heteroatoms in line with the rest of the condensed formula, and there's a very specific implication when we do this. The implication is that the carbon is doubly bonded to the first heteroatom in the chain and singly bonded to the second heteroatom in the chain. This is the convention. Whenever we see a carbon followed by 2 heteroatoms, it is always assumed to be doubly bonded to the first heteroatom and singly bonded to the second heteroatom. This fits with the ester. Carbon number 2 is doubly bonded to this oxygen and singly bonded to this oxygen. Continuing on with the formula, we have 2 CH2 groups before we get to the next carboxylic acid derivative. Pause the video for a second, see if you can figure out how we would write the next carboxylic acid derivative in this condensed formula. We start with the carbon atom, and the convention says we write the first heteroatom as the one that is doubly bonded, and the second heteroatom is the one that's singly bonded. This carbon is doubly bonded to oxygen, so we write the oxygen first, and then the nitrogen. The nitrogen has a hydrogen of its own, and then we finish the molecule out with the CH3 group. To do this amide functional group, we say that it's doubly bonded to this first oxygen and singly bonded to this nitrogen. This is the convention for carboxylic acid derivative. Our last example happens to be one of the hardest ones for students to comprehend, and that's the difference between an alcohol at the end of a chain and an aldehyde at the end of a chain. For this first molecule, we would start with the CH3 group and the CH2 group. The OH group is in line with the rest of the carbon backbone. There's nothing after it, so we would just write it in line with the rest of the molecule. We don't need any parentheses when it's in line with the carbon backbone. The alcohol at the end of this chain is written CH2OH. For the aldehyde, we'll start off the same way. We'll start off with the CH3 group and then the CH2 group, but how we write the aldehyde is going to be a little bit different than how we write the alcohol. We start with that carbon to which the aldehyde is attached. If we were to write the oxygen and the hydrogen and we wrote COH, that looks a lot like the end of an alcohol, and that gets confusing. So we don't do that. We have a special formulation, a special tradition for how we write aldehydes at the end of a molecule. And that convention says we start with the carbon and then we write the hydrogen before we write the oxygen, CHO. CHO is the convention for an aldehyde at the end of a condensed formula. There's not a good rhyme or reason from the structure why we write it this way. It doesn't follow the same rules as the acid derivatives. I suspect we wrote the aldehyde as the CHO specifically to avoid confusion with an alcohol at the end of the molecule. When I see CH2OH, I know that's an alcohol, but when I see it inverted, I have to stop and think, why is it inverted? And it's inverted like this because it's an aldehyde, not an alcohol. To highlight the difference between these structures, CH2OH, carbon makes 4 bonds, 1 bond to the previous carbon, 2 more bonds to hydrogen, and then the bond to oxygen and the alcohol. This is how we would write an alcohol in a straight chain molecule. Contrast that with a very specific formulation for an aldehyde. Carbon makes 4 bonds, it's making 1 bond to the previous carbon, 1 bond to the hydrogen, and that still leaves 2 more bonds, and then it's oxygen on the end. Oxygen also makes 2 bonds. This formulation tells us the oxygen is doubly bonded to the carbon as part of the aldehyde function. This tends to be the one that students end up missing the most. This is the hardest one to remember, so go ahead and make note of this now. With these tips and tricks under your belt, you can be an OChemNinja when you write condensed formula too.
Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists and see what you like. As always, don't forget to like and subscribe.